Hi everyone, let's continue. Let's talk about linear approximations written using increment notation. So we call on the tangent plane, we have z equals f of AB, the points, and then plus partial f partial x evaluates at AB times the linear vector x minus a plus partial f partial y evaluates at AB times the linear vector y minus b. So we can rewrite this as z minus f of AB equals partial f partial x times x minus a plus partial f partial y times y minus b. And in the increment notation, well, this guy is change. This guy is the change of z, right? And this guy is the change of x, and this guy is the change of y. All right, and then notice that now we have change of z equals f of partial f partial x times change of x plus partial f partial y times change of y. This is the same as the dot product of the two vectors. The first vector is partial f partial x, comma partial f partial y. The second vector is changing x, comma changing y. So the first vector, partial f partial x and partial f partial y, we call it the gradient of f at AB. So the notation, so this guy means change, okay, change in the quantity. But this guy means the gradient, okay? So the upside down triangle denotes the gradients. So yeah, make sure you're sure about you know what is the triangle, what it represents. Okay, so yeah, it is denoted by this symbol upside down triangle. Suppose we start at the point AB in the domain of a function f of xy. If the input values x equals a changes by run x, and the input value y equals b changed by a run y, then the corresponding rise on the tangent plane is given by change of z is the gradient vector dot product with the vector of change in x and change in y. Okay, so now we can say the run vector. So it's running in two directions, right? X and Y direction. So the run vector, we can use it as this notation. Well, be careful. This guy, we have an arrow on top of it. So this guy is a vector. And change of x with no arrow on top, this is just a component of that run vector. Okay, so if the run, we can use the vector to denote, then the rise in the tangent plane is change of z equals the gradient vector dot product with the run vector. Okay, so the linear approximation in terms of gradients is the dot product of the gradient vector and the run vector. Okay, so keep this in mind. Let's look at the following example. So let f of xy equals x squared minus xy plus y squared minus y. A, find the gradient vector. Okay, so what's partial f partial x? Derivative of x squared is 2x. Derivative of x is 1, so minus y, and then there's no x in the y, okay, so the derivative of y squared minus y is 0. And then fy is the derivative of x squared is 0, and then the y is 1, so we have minus x plus 2y minus 1. Okay, so our gradient vector equals the x coordinate is 2x minus y, the second coordinate minus x plus 2y minus 1. And then when we evaluate at 1 minus 1, we get 2 times 1 is 2, minus -1, so +1. -1 plus 2 times -1 minus 1. So we have 3, and then we get -4. So far, so good, everybody. Part B, find the constant so that the vector 2, 4, c is tangent to the graph of z at the points 1, -1, f of -1, 1. Okay, so what do we do here? Let me draw a picture. So here we have, suppose we have a surface, and then this is the tangent plane, right? And then we have a normal vector. So let's say, let me use a different color here. Let's say this is the vector u. U is tangent to the graph. Okay, what does that mean? Well, it means u is in the tangent plane, right? And furthermore, from this picture, we know and is perpendicular to u, so their dot product should be 0. Okay, and u equals 2, 4, c. And what is n? Okay, and remember that equals minus fx minus fy and 1. Why is that? You go back to our notes. Okay. See? The normal vector is minus partial f partial x. So here, minus, what happened? Okay. It's here. This is the normal vector. Minus partial f partial x, comma, minus partial f partial y, comma, 1. Okay, so that's normal vector. And where are we? Okay, here. So, at the point 1, -1, okay, we already know that because from the gradients, we know gradients, the coordinates are partial f partial x and partial f partial y. So we know that this guy is partial f partial x evaluates at -1, 1. And this guy is partial f partial y evaluates at -1, 1. So the n is -3 minus -4 give us 4, and then this is 1. So dot product, so u, the dot product n dot u equals -3 times 2, 4 times 4, and c times 1. That equals 0. So c equals 3 times 2 is 6, move to the other side, become positive. 4 times 4 is 16, but move to the other side, become negative. So c equals -10. Alright, how about part C? Suppose we start at a point and we move to another point. Use linear approximation to estimate the change. Okay, so what is the run vector? Okay, so we use the final point minus the initial point. Okay, so that's change in x and change in y. So 1 minus that, okay, 0.001. And this guy, minus -1 is like +1. It becomes minus 0.02. So change of f equals the gradient dot this run vector. The gradient 3 minus 4 dot 0.001 minus 0.02. So that is 3 times 0.001 minus 4 times negative 0.02. What is that? Okay, This is 0.003 minus negative become plus 0.08. So the answer is 0.083. So far so good, everybody. So this is the change. This is okay. This is approximated. The change of f is approximated by this. So far so good, everybody. Okay. Let's continue to look at the properties of gradients. Okay, our next goal is to study some very basic but very important properties of the gradients. So the gradients is partial f partial x, comma, partial f partial y. So note that if f is a function from R2 to R, then the gradient is a function from R2 to R2. Okay, the output is also a vector in R2. So some goals for this session are to investigate how the gradients are represented graphically, how gradients are related to the directional derivatives. Okay, so we will explain what is directional derivatives, okay, later. And then how gradients are related to the level set. So first, let's look at how we can represent gradients graphically. So let f of x equals x squared minus y squared. Let's compute the gradients at the specified points and plot them. Okay, so here, what is fx? Fx derivative of x squared is 2x. And then what's the derivative of respect to y? Well, the x squared has no y, so the derivative is 0. Minus y squared, the derivative is minus 2y. So at the point 1, 1, we plug in x is 1 and y is 1, we get 2, negative 2, right? At the point minus 1, 1, well, x is minus 1, so minus 2, and then y is 1, so minus 2. Minus 1, we get minus 2, and minus become positive. 1 minus 1 give us 2, and minus negative become positive. Okay, what does that mean? At the point 1, 1, the vector, the gradient vector is 2 minus 2. Well, 2 here, negative 2 right here. So this is the picture, right? It's standing at the point 1, 1 with the vector is 2 minus 2. And then at the point minus 1, 1, the vector is negative 2, which is this guy. At the point minus 1, the vector is minus 2, 2, so this guy. At the point 1, minus 1, the vector is 2, 2, so this guy. So far, so good, everybody? All right. So you can see the arrow here, if we use the scale of that vector, it really sometimes give us very big arrow. So then we have the arrow cross each other. Okay, do you remember slope field we learned in Calculus 2? So sometimes the slope field, we can scale the slope, the vector to be smaller number, so that we have a lot of like smaller segments, help us to understand how the flow, what the flow is, right? But here we can do the same thing. We can also rescale the vector, so to make it more tiny, then they won't cross each other. Okay, so computer generate plots of the gradients. So still we have a tiny sample set, right? Otherwise it's too much clutter. Okay, the length are not to scale, so this is necessary to to avoid arrows overlapping each other. Okay, because you don't want to have the case like what we did. You don't want them to like overlap. No. And exactly how the length are rescaled depends on the software. In any event, arrows that should be longer are longer. Okay, you can look at this picture. So these guy arrows are longer and this guy arrow is shorter. Okay, then you know this guy, the gradient vector, it has bigger magnitude compared to this guy. So far, so good. But you can see the directions. So from this picture, you can tell here we're going this way, here we're going that way, and then here we're going this way, here we're going this way. Okay? And here we're going this way, here. Let's see, going this way, and this way. So far, so good, everybody? Okay, we'll now look at several functions f of x, y, along with their graphs and gradient plots. Here are some guiding questions you should ask yourself as we proceed. What can we say about the direction of the gradient? What can we say about the magnitude of the gradient? How is the gradient related to the level set of f? Okay, so keep those in mind. Look at the following. So consider the function f of xy equals x times e to the minus x squared minus y squared. Well, this is the graph, okay? You can see this is a graph in a three-dimensional space. And then here is the gradient. So gradient function is like a vector field on the xy plane. So this is on the xy plane. Okay, it's a two-dimensional. Okay, on the xy plane. So here, okay. Now let's see what happened. You can see this guy that corresponds to, and this guy corresponds to this guy. Okay, and okay, what can you see from this picture? Look at those arrows. You see the arrows is going from the lower place to the higher place, right? From this picture, you can see this guy is higher, with larger z values, and this guy is lower with the lower z values, right? So we can say the direction point to where f increases, right? Okay. And furthermore, can you see this guy, the arrow is bigger, and then this guy, the arrow is smaller? Okay. That is because here you can see this place, the f increases more rapidly than here. Okay, so here or there, the f increases, almost don't change, okay, or increase slower. Okay, so we can see the magnitude is larger when the f increases more rapidly. Okay, and it's smaller when the f doesn't increase so rapidly. Let's continue to look at the next example. So consider the function f of xy equals x minus y. The gradient plots also display level set. So here, let's see. You can see, I think this picture kind of rotates a little bit. Okay, so let's see. This is the x and this is the y. So the arrows, I think there's maybe the orientation. So we should flip this. Okay, so because the arrows should be pointing to where the f increases, but here it looks like go down. So maybe because this picture it's rotated 180 degree. Okay, so it doesn't really match the current positions. Okay, 3D picture we can move it, so yeah. Okay, but looking at this function, and you can see the gradient of f, derivative of f with respect to x is just 1, derivative of f with respect to y is -1. So 1 minus 1 is going down, right? And so this is the x-axis, this is the y-axis. Okay. And on the 3D picture, this is x-axis, this is y-axis. So our picture, the x is here, y is on top. So it's like we use this guy, we rotate until we reach here. Then this picture will match with it. So far so good, everybody. All right. What do I mean is, if you rotate it here, then this is x, this is y, and this is z. Then how would this change? So we will have this guy here, and then something like this. Okay, but it's hard to see. It's more obvious to see what happened with this picture. Okay, but anyway, I want to explain to you that in this case, gradients also point to the direction where the f increases. Okay, and you can see here the length of the gradient at different points is the same. So that is because this is a plane. Okay, f increases with the same speed at any point on the plane. So that's why we have a constant vector field on the xy plane for the gradient. Next, let's continue. So consider the function x squared, okay? While x squared, this is on the xz plane, right? Xz plane. So you can see this is like a cylinder because the y is a free variable, okay? And if we find the gradient is just 2x, derivative of x squared is 2x. There's no y there, so derivative of y is, with respect to y, is 0. And you can see here, we increases, okay? So that's why we increases in this direction. And when we're near the y-axis, f increases slowly, and when it's far away from the y-axis, the function increases more rapidly. So far so good, everybody. And you can see those this graph does not depend on the y value, okay? Because this guy has no y, so y doesn't matter. No matter what the y is, this guy and this guy are the same, right? Okay, let's continue. So consider the function x squared plus y squared. The gradient plot displays level set. So do you still remember what's level set? Let's say if z equal to 0, that corresponds to the origin. When z equals to 1, x squared plus y squared equals 1, that gives us a circle, right? When z equals 2, x squared plus y squared equals to Well, maybe we should pick z equals 4. We pick z equals 4, and then x squared plus y squared equals to 4. That is a circle with radius 2. Okay, so this picture also includes the level set. Now, look at the gradients. The gradients of x squared, partial f partial x of x squared is 2x. Partial f partial y is 2y. And when we plot this, what can you see here? If the point is near the origin, then the arrow is smaller. When it's far away from the origin, the arrow is bigger. Okay, and that makes sense with the graph, because when it's near the origin, f increase slowly. When it's far away from the origin, the f is increasing more rapidly. And furthermore, I want you to compare the level curves and the gradients vectors. Can you see it's perpendicular to the level curve? Can you see? So actually, this is true. The gradient vector is perpendicular to the level set. Okay, let's continue. Consider the function f of xy equals x squared minus y squared, and this is a picture of the surface. And then for the level curves, you can see when we use a plane here to cause it, then we have these two. So these two level curves, that's why you can see those values are positive, right? And when we pick the z is 0, okay? If z is 0, then we get this line and this line. So when we pick z is 0, we get these two lines. And furthermore, if we pick z is negative, then we have this guy and that guy. So that corresponds to this guy. So you can see the z values are negative. Okay, so that is the level curves. And then how about the gradients? You see, when it's near the origin, the gradient, the length of the gradient vector is small because the function does not increase rapidly, right? It increase or decrease slowly. When the point is far away from the origin, then f change the values more rapidly, either increase or decrease. And you can see the arrows. So here it goes, the arrows go from here to there, because this is how the f increase, right? This is how the f increase from smaller values to larger values. Okay, and furthermore, can you see the arrows of the gradient vectors is perpendicular to the level set? Yes, so it's perpendicular, see? Perpendicular to the level set. Let's continue. So let's consider 3 issues using more precise mathematics. We call that to measure the steepness of the graph of f at a point in some direction u. Okay, assume u is unit vector. We use the directional derivatives. Okay, I should remove the words we call this, because we will learn this in the next session as well. Okay, so here we use directional derivatives, which we denote by du of f evaluated at AB. The slope of the surface z at the point P in the direction of u is given by the following formula. Okay, so we know that the slope in the x direction. Okay, so we know the slope in the x axis direction is fx, right? And we know the slope in the slope of the surface in the y-axis direction is Fy. Okay, what happened? So if we draw the picture, so this direction will get the slope is Fx. This direction, the slope is Fy. What happened if I want to get in general just any u? Okay, in any direction. Let's say this is the u. Okay, this is the u. Then what is the slope? So it turns out that the slope in the direction u, here we assume u is a unit vector. Okay, we want to just represent the direction, and the magnitude of it is 1. Okay, and the directional derivative, which is the slope in the u direction, is given by the gradient vector dot u, the vector u. Okay, so this is the slope in the u direction. Okay, and here we assume u is a unit vector. It means the magnitude of the u is 1. Okay, general questions. How does this directional derivative change when we fix the point P and we rotate u? So let theta be the angle between the gradient vector and the vector u. Then we know that, so in general, if u is not okay, so if u is not a unit vector, then the gradient, then the directional derivative equals to the gradient. So here we know this is the gradient dot u, and that means is the magnitude of the gradient vector times the magnitude of u times cosine theta. Okay, let me see. Okay, so I want to say this formula, it works. So I want to say these formula works in general. We don't require u to be a unit vector. But now at this step, if u is a unit vector, then the magnitude of u is 1. Then we plug in 1 here, we just get the gradient of f, the length of that, times cosine theta. All right. So more specific questions. What are the maximal and minimal possible values of the directional derivatives when u varies? Okay. Let's see. Okay. So when u varies, how does this change? Okay. So you can see if theta equals 0, then what do we have? Cosine 0 is 1, then the directional derivative will equal to the length of the gradient vector at P. Okay? And this is we get the maximum values. And if theta equals pi over 2, then cosine theta is 0. So the directional derivative is 0. Okay? If theta equals pi, then cosine pi is -1. The directional derivative will equal to negative of the length of the gradient vector at P. Okay, so for what unit vector u will this guy be maximum? Okay, when u, okay, so when u and the gradient of f are in the same direction. right? Because theta equals 0. That means they're in the same direction. And what would this vector, to make the directional derivative be minimal? Well, if they're of the opposite direction, okay? So when u and gradient of f are in the opposite direction. In what direction will the directional derivative be 0? Well, when they are perpendicular. So u is perpendicular or orthogonal to the gradient vector. So far, so good, everybody. Okay, how do we know the gradient vector is perpendicular to the level set passing through P? Okay, so let's look at, let me draw a picture here. Okay. So let me draw some pictures. So we have, let's say this is a level curve. Okay, so this is a level curve f of xy equals 0. Okay, and well, this is the gradient. Okay, so gradient of f equals fx, fy, right? And let's say the curve goes this way, then we have, this is the tangent vector, right? So this is tangent vector v. And if we want to show the gradient vector is perpendicular to the level set, it's the same as to show that the gradient vector is perpendicular to the tangent vector. Is that okay? Because the tangent vector tangent to the curve, to the level set. And so what is the tangent vector? Well, the tangent vector will be, because this is a curve in the xy plane, right? And we talked about in the beginning of this session, if we let the x component be 1, then the y component, the rise, will be the slope, okay? Which is the first derivative. So this is dy dx. Is that okay, everybody? And do you remember that we have a fact showing that dy dx? So if y is a function of x implicitly, okay, then dy dx equals minus fx over fy. Do you remember that? We showed that in last sessions when we used chain rule. Okay, we differentiate this guy with respect to x. Okay, we consider y as a function of x. We take the derivative with respect to x. Then we have fx dx is 1 plus fy times dy dx. That is 0. So that's why when we solve for dy dx, we get this formula. So dy dx equals, so that's why x component is, first component is 1, second component is minus fx fy. Now let's see. Gradient dot this tangent vector, we have fx times 1 plus fy times negative fx over fy. Now what happened? Fy cancel. Oh, then we have fx minus fx. That is 0. It means the gradient is perpendicular to the tangent vector. Well, this tangent vector tangent to our level set. So it means that the gradient vector, sometimes I forgot to use the arrow symbol. So it means the gradient vector is perpendicular to the level set. So this is the idea. So far, so good? Okay, so here I put down a summary of the basic properties of the gradient. So suppose that the gradient vector is not the 0 vector. Okay, if it's 0, then you cannot talk about its direction. Okay, now assume it's not 0. Then the direction of the gradient vector is perpendicular to the level set of f that passes through the points A, B. The direction in which f increases most rapidly. right? We show that in a lot of examples when we see the picture of the surface and the level curves and gradients field. Okay? The magnitude of the gradient is the maximum directional derivative of f at AB, right? We just show it here. The directional derivative, the big maximum will be the magnitude of that. The minimum will be the negative, the magnitude of that, of the gradient vector, right? Okay, so the maximum, okay, and is larger when the level sets are closer together and small when they are far apart. Okay, why is that? So that is because, do you remember if u is a unit vector, then the directional derivative at f equals to the gradient vector times cosine theta. Theta is the angle between u and the gradient vector, right? So if the level sets are close, which means f changes rapidly. Okay, so it changed rapidly, then the slope, okay, in any direction, slope, so slope is big, okay? It's either positive or negative. If positive, if it's increasing, negative is decreasing, but the magnitude, the magnitude of the slope is big, okay? So that's why the gradient, the slope and the length of the gradient are kind of related, okay? So that's why the magnitude of the gradient is also big. Okay, and if the level sets are far apart, that means f changed slowly, and the slope is small. So that's why the magnitude of the gradient field is also small. So far, so good, everybody? Okay, continue. Additional facts. Minus gradient vector, okay, this is the opposite direction of the gradient vector, points in the direction of the maximum rate of decrease. See, decrease. If it is negative, that is the direction of the maximum rate of decrease. The directional derivative is 0 in the direction perpendicular to the gradient vector. Okay. All right. Let's continue. Let's look at this example. Yeah, we talk about a lot of theory. It's good to work on some examples. So let f be this function and let p be the point 1 minus 1. Write down the equation of the level set that passes through p. So let's see. F of 1 minus 1 equals 1 squared is 1 minus 1 times minus 1 become 1 plus 1. Let me do it slowly, okay? Minus 1 plus minus 1 squared minus negative 1. Oh, so that's 1 plus 1 plus 1 plus 1, which is 4. So far, so good, everybody? So what is the level set? Sometimes people call level set, sometimes people call level curve. They're the same thing. So that is the function equals 4. So this is the level curve. So far, so good, everybody? B, find a vector that is perpendicular to the curve at the points P. Well, we know that the gradient vector at minus 1 and 1 is perpendicular to the level set. Okay, perpendicular to the level curve as well. Same thing. So it's enough to just find the gradient vector, evaluate at that point. So the gradient vector equals, well, to the derivative with respect to x, we have 2x, y, and then with respect to y, we have negative x, 2y, and minus 1. Is that okay, everybody? And then when we plug in 1 and minus 1, we have 2 minus -1, so 2 plus 1, minus 1 plus 2 times -1, so minus 2, minus 1. So this is 3 minus 4. Okay, so this is the vector. This is a vector that is perpendicular to the curve at the point P. So far, so good. Part C, find the unit vector that points in the direction of maximum rate of increase. Well, maximum rate of increase, that is the direction of the gradient vector, right? But however, this is not a unit vector. So what is the magnitude of that vector? Well, that is 3 squared plus -4 squared. We know special triangle, side, right angle triangle, 3, 4, then the other side is 5. So, okay, the unit vector in which the direction of maximum rate of increase will be in that direction, because we want unit vector, so divided by the length. Okay, so we have 5/5 minus 4/5. How about in the direction maximum rate? So direction maximum rate of decrease is the opposite direction of what we get before, right? So negative of what we had before, this guy. Then now we have -3/5, and now it's positive 4/5. Is that okay, everybody? Find the unit vector that points in the direction of 0 rate of change. Okay, so this guy, what do we need? Okay, so we want to find a unit vector. So let's say u equals AB, and we want to have u is perpendicular to the gradient vector, right? Because we need 0 rate of change. So we need u dot change of gradient vector equals 0. So what do we have? 3a minus 4b is 0. And also, because u is a unit vector, a squared plus b squared equals 1. So far, so good, everybody? Okay. And how do we do it? We can use substitution, right? Here, I don't have enough space, so let me continue here. Okay, sorry about that. From the first equation, we can solve for a. We move the 4b to the other side and then divide it by 3. Then we use substitution method, so we can plug into the second equation. Then a squared, so 16b squared over 9 plus b squared equals 1. On the left, we take the common denominator 9, and then 16 plus 9 is 25. So b squared equals, multiply by 9 on both sides, then divided by 25. Well, then b equals plus or minus, take the square root, so 3 over 5. Then a is 4, so which means plus or minus 3 over 5 times 4 over 3. Okay, then so this is plus or minus 4 over 5. It means the vectors are, if a is positive 4/5, then b is 3/5. If a is negative 4/5, then b is negative 3/5. Okay, everybody? My arrow is quite long. Okay, let me use this arrow. And can I move this little bit? Oh, okay. I can't. Okay. So we have two unit vectors that are in the direction of 0 rate of change. Okay, so which is perpendicular to the gradient vectors. So here are the two vectors. So far, so good, everybody. Okay, next illustration. Water streams in a topographical map. So water running along a slope surface tend to flow in the direction of steepest descent. So water tends to flow in a direction opposite to the gradient of the altitude function. So we would expect water to flow perpendicular to the contour on a topographical map. Okay, so you can see last time we talked about those lines, the level curves or level sets. Okay, so the gradient will be denotes the direction where F increased rapidly. Then how will water flows? So water will flow in the opposite direction with the gradient vector. So which means, okay, so water will flow like this here. Okay, let's see here. So this is water. So you can imagine water flows in the direction of negative gradient F. So far so good, everybody. And you can see all of those blue lines, they are waters. And you can see almost all of them are perpendicular to the level curves, because this is how water flows more rapidly to the steepest to the decrease, okay, in the direction of the steepest descent. Okay, water flows down, okay, where the height function decreases rapidly. Okay, so let's continue in video part C. All right, so see you soon. Bye.